Welcome everyone. This is the 14th chapter of the crystal clear electronics video series titled Twilight Switch, Simple Sensors and Comparator. As the title suggests, we'll be discussing simple sensors, optoelectronics, comparators and much more. Today's presenter is Viktor Vincze. Viktor, would you introduce yourself?
Thank you very much for the introduction to Bence. I'm Viktor Vincze, a qualified electrical engineer and one of the authors of Crystal Clear Electronics. I currently work as a project manager in a medical device development company. To balance my long hours in front of the computer, I spend a lot of time doing sports in my free time, so my sports watch is very useful to me. A sports watch like this has a lot of sensors crammed into it by the developers. I wonder if you could identify the sensors shown in this video that can measure heart rate.
The 14th chapter was written by Miklós Szilágyi and Erzsébet Szomorú-Osváth. Before you can control your devices by temperature, light, or proximity, let's recall how FETs work with a simple circuit. However, before working with FETs, there are a few things to keep in mind.
That's right. FETs are very sensitive components. Always check the maximum voltage and current ratings in the datasheet before using them, and make sure to never exceed these values, as it will destroy the device. Also, they're very sensitive to electrostatic discharge. An electrostatic discharge, or ESD in short, happens when an electrically charged object touches the FET. The human body can be electrically charged as well, usually by some form of rubbing, for example, from rubbing your clothes and a chair or between the soles of your shoes and the floor. To protect the component from ESD after removing it from the ESD safe package, place it onto the package and keep it there until it's not used, and only remove it when you install the component into the circuit. When removing, touch the package first and only then the component, as this ensures that the pouch and the component on it will be at the same potential as us. The figure shows the ESD safe package containing the FET. There's a wide variety of casing for FETs. The most widespread through-hole and surface-mounted designs have three terminals. These are the gate, the drain, and the source. The order may vary from type to type, so it's always worth checking the datasheet of the given component. The most common through-hole casings are the TO92 and TO220 casings. All of these have three terminals. On the casing of the TO220, we can find a large metal surface, which helps cool the component. This metal surface is usually connected to the drain pin, but always confirm this in the datasheet instead of making assumptions. From the SMD, that is the surface-mounted designs, the SOT23, DIPAC, double DIPAC, and SO8 are the most common ones. If there are more than 3 pins, it may occur that the drain and source are connected to multiple pins or multiple FETs can be found in the casing. An important distinction is that these devices are controlled by voltage, unlike bipolar transistors, which are controlled by current. For the sake of simplicity, we can imagine the FET as a voltage-controlled switch. As our first example, let's turn on an LED using an N FET. The voltage controlling the FET is coming from an adjustable voltage divider circuit. If you look at the schematic, the operation of the Q1 MOSFET is the following. If we increase the voltage between the gate and the source pins of the device above a certain threshold, called the forward voltage, the resistance between the drain and the source pins decreases and the device starts to conduct. When this happens, current starts to flow through the LED and the series current limiting resistor, and as a result, the LED lights up. When the MOSFET's gate is on the same or lower potential than the source, the resistance between the drain and the source is so high that it effectively acts like an open circuit. This means that current cannot flow through the circuit and the LED stays off. To demonstrate this, we have also built the circuit on a breadboard. Could you please show us how it works, Bence?
Of course. As you can see, the output of potmeter 2 is connected, which means it acts as a variable resistor. The resistance between the outlets will increase as you rotate the shaft towards the left. The voltage divider consists of the potmeter and resistor R2. When the potentiometer is turned all the way to the left, about 1 volt is applied to the gate, which is not enough to turn on the MOSFET. As I start to reduce the resistance of the potmeter, the voltage across resistor R2 and consequently the gate increases. If I reduce the resistance enough, the gate source voltage rises above the threshold voltage and the MOSFET starts to conduct and the LED lights up. We can also test the circuit by using something requiring more current for the operation, in this case with a DC fan.
In the schematic seen in figure 6, we have removed the current limiting resistor, and instead of the LED, we control a 12-volt DC fan. To protect the transistor from the inductive voltage surge that rises when the motor is switched off, it's crucial to install a diode in parallel with the inductive load. In our case, this is not necessary as the fan already includes the diode. However, it's important to keep this in mind or otherwise the transistor may fail. In this case, the same thing happens as before with the LED, that is, if the gate voltage is at least 3 volts higher than the source, a low resistance is created between the drain and source outputs of the transistor, approximately a short circuit, which causes the voltage on the fan to increase, and because of that, it starts spinning. If the gate source voltage drops below the threshold voltage again, the fan stops. The resistance of the FET depends on the gate source voltage, so if you want to use it as a switching element, it's wise to choose the highest possible voltage within the allowed limits, which can be read from the datasheet. By controlling the gate source voltage with the voltage divider, made from R1 and R2, we can control the MOSFET's drain source resistance. We have to pay attention to the temperature of the MOSFET, because if it is not fully open or fully closed, a considerable amount of energy will be dissipated on the device, causing it to heat up. In some cases, a heat sink is also used to help the MOSFET dissipate heat better, or another option is to reduce the power dissipated by the FET.
In this case, a change in the MOSFET's resistance becomes perceptible. We have also replaced the LED with the fan, so we can see that turning the potentiometer changes the speed of the fan, that is, changes the drain source resistance of the MOSFET. After FETs, let's move on to the world of sensors. First, let's explore some unique types of resistors that can be used as simple sensors. First up, we will discuss photosensitive resistance, also known as photoresistance. I would like to ask Viktor to take the floor.
Thank you, Bence. The photoresistor, in other words light-dependent resistor, is a resistor which is made out of semiconductor material. This component changes its resistance when exposed to light. However, it doesn't behave the same way with every kind of light, so the parameters below are very important in the datasheet. The spectral peak is the wavelength of the light to which the device is most sensitive and changes its resistance to the greatest extent. The photoresistance is the resistance of the device under certain lighting conditions, and the dark resistance is the resistance of the device without any light.
It's interesting, the photoresistors have a relatively short response time, failing to track lights that flash faster than about 10 Hz.
The illumination resistance characteristics of a photoresistor depends on the composition of the semiconductor. The PGM5506 photoresistor, which we will use, has a negative characteristic, meaning that if the illumination increases, the resistance decreases. The datasheet specifies that under 10 lux illumination, which is approximately twilight illumination, the resistance value ranges between 2 and 6 kiloohms. This data is crucial for designing the circuit, which we did in such a way that the base current of the transistor changes from completely dark to general room illumination. Take a look at the following transistor circuits. The photoresistor controls the base current of the transistor, which, in turn, causes the collector current to change. This change in current alters the LED's brightness. Let's examine the NPN transistor example in more detail. For Q1 transistor to conduct, the voltage between the base and the emitter has to be higher than the forward voltage. This is usually around 0.6 to 0.7 volts, and it changes a little because of the base current. As we learned previously, the transistor is a current-controlled device, and the flow of current through the collector can be controlled by the base current if the voltage between the base and emitter is above the threshold voltage. The function of R1 in the circuit is to set the lower threshold of turning on. When the transistor is not conducting, which means no current is flowing through either the collector or the base, add R1 and R1 form an unloaded voltage divider. Therefore, we can apply the familiar voltage divider formula. As we can see, R1 has the same voltage drop as the base emitter junction. Because of this, we can calculate the value of all the R1 required to turn on the transistor. We will choose R1 as 100 ohms for simplicity, and then use the voltage divider formula for the common point of all the R1 and R1. It is important to remember that now the unknown value is not the voltage at the output of the divider, as we are specifying it as the forward voltage, which is about 0.7 volts. Rather, we are trying to find the value of LDR1. Therefore, we need to rearrange the equation and solve LDR1. Upon calculating the formula, the result shows that to reach the specified forward voltage, LDR1 needs to be 1.6 kilo ohms. Since there is current flowing through the base of the open transistor, through the voltage divider, we can no longer use the unloaded divider formula. Instead, we can take advantage of a property of the transistor. As soon as the base emitter junction of the transistor reaches the forward voltage, the voltage across R1 will only change by a negligible amount. Because of this, the base current will be determined by the resistance of LDR1. According to the formula, you can see that the base current and the resistance of the LDR are inversely proportional. A brighter illumination will result in a smaller LDR resistance and a higher base current, which makes the illumination and the base current directly proportional in the end. The transistor amplifies the current. The collector-emitter current will be beta times higher than the base current. Since we have an LED in series with the collector-emitter junction, this current will flow through the LED as well. We have just made a circuit where the LED shines brighter if the illumination is brighter, just like the backlight of a phone screen. Bence, could you please show us the circuit?
Of course. You can see that as soon as I cover the resistor, the LED goes out.
If you replace the LED with a buzzer, we have created a simple light-sensitive alarm. I'm not sure if we are ready for this, Bence. What do you think?
Ready. It must be wonderful to wake up to this in the morning. We can already measure brightness with great accuracy, but knowing the temperature would also be helpful. However, we have a solution in the form of a special resistor that allows us to measure temperature. This is a component none other than the thermistor.
The components we are about to introduce change their resistance with temperature. NTC means negative temperature coefficient. That is, the resistance will be inversely proportional to the temperature, while PTC means positive temperature coefficient, meaning that the resistance will be directly proportional to the temperature. The circuits in figure 9 from the previous section also work great if we swap the LDR to an NTC. In our next circuit, we'll combine the bipolar transistor's current amplification and the switching of the MOSFET to make a temperature-controlled circuit with adjustable sensitivity. Imagine a room where you want to control the ventilation automatically based on temperature. The NTC acts as the heat sensor, the R1 potentiometer is used to set the threshold temperature, and the task of Q1 and Q2 is to operate the fan. When the NTC starts to heat up, its resistance decreases, which causes the base emitter voltage of Q1 to increase until it reaches the forward voltage of around 0.7 of a volt. At that moment, current starts to flow through the NTC into the base, which gets amplified and generates a collector current. The emitter current, which is the sum of the collector and the base current, creates a voltage drop on resistor R2, which is equal to the gate source voltage of the Q2 MOSFET. If this gate source voltage exceeds the threshold voltage of the MOSFET, it starts to conduct, and the fan will start to spin, creating airflow. The process finds a stable operating point based on the external temperature, the airflow of the fan, and the position of the potentiometer. To achieve faster switching, the R1 potentiometer creates positive feedback. As soon as Q1 starts to conduct, the potential at the emitter of the Q1 starts to rise. Since the third pin of the potentiometer is connected to the emitter of Q1, the voltage on the second pin will start to rise as well, opening Q1 further, causing a higher collector current, which increases the voltage of the emitter even more, and so on. The potentiometer enables us to set the temperature threshold of this circuit. If we use a PTC instead of an NTC, the operation will be the opposite, meaning that a falling temperature will cause the circuit to turn on. If we swap the fan to a heating element, such as an infrared lamp, we get a simple automatic heater. We've now reached the end of a relatively lengthy section. Before the following video, Bence would like to show you a circuit. We have stopped several times while filming, and if you have time, I ask you to stop and build the circuits in each section, because that's where you can learn the most. Bence, would you mind demonstrating this circuit?
To help you observe the rotation of the fan more clearly, we have placed a small sheet of paper on it. The paper is black with a small white strip. So hopefully you can see the rotation better. The fan operates the following way. When the NTC is heated, the fan starts spinning after a short period. Similarly, when the NTC cools down, the fan stops after a while.
It was nice to see that last circuit in action. Temperature sensors can also be found in almost all our devices, for example in our phones or smartwatches. They help measure the temperature of the body or the environment. My sports watch, for example, also evaluates the environment's temperature during exercise and takes it into account when monitoring my workout.
I believe this episode has been informative, so we'll say goodbye for now, but we'll see you again soon.